Chapter 8. AI Technologies and Platforms. 8.1 Overview of AI Technologies. Artificial intelligence, AI, encompasses a suite of technologies with the capability to mimic human cognitive functions. It is pivotal in transforming innumerable sectors, leveraging data to facilitate informed decision-making, streamline operational efficiency, and foster innovative solutions. AI can be categorized into two primary types: narrow or weak AI, which is designed for specific tasks, and general or strong AI, which has the theoretical potential to perform any intellectual task that a human can. Though general AI remains a largely theoretical concept, narrow AI is prevalent across various industries, ranging from customer service automation via chatbots to diagnostic assistance in healthcare. Among the technologies underpinning AI, machine learning, ML, is a cornerstone, where algorithms improve automatically through experience and the use of data. ML can be further divided into subfields, such as supervised, unsupervised, and reinforcement learning, each applicable in different contexts and scenarios. Supervised learning algorithms are trained on labeled datasets and aim to predict outcomes or classify data based on past examples. They are widely utilized for applications such as speech recognition, image classification, and email filtering. Unsupervised learning, on the other hand, deals with labeled data, identifying hidden patterns or intrinsic structures within the input. It is often used for anomaly detection, market basket analysis, and clustering tasks. Reinforcement learning is a paradigm in which algorithms learn to make sequences of decisions by interacting with an environment, typically used in robotics, game playing, and navigation. Deep learning, a subset of machine learning inspired by the structure and function of the human brain, has gained tremendous traction. It employs artificial neural networks with multiple layers of processing units, allowing for the modeling of complex and high-level abstractions in data. Deep learning has been the driving force behind significant advancements in areas such as natural language processing, NLP, and computer vision. With NLP, machines are able to understand and respond to human language in a way that is both meaningful and contextually relevant. Computer vision, the machine's ability to interpret and make decisions based on visual data, has seen practical applications in autonomous vehicles, facial recognition systems, and medical image analysis. Another important AI technology is robotics, which involves the design, construction, and operation of robots, often enhanced with AI to perform tasks autonomously. AI-equipped robots can learn from their environment and improve their performance over time, making them valuable in manufacturing, space exploration, and domestic use. Similarly, expert systems, which emulate the decision-making ability of a human expert, have made it possible for machines to provide consultation like a human expert in fields such as medical diagnosis and geological exploration. Cognitive computing involves creating systems that simulate human thought processes in complex situations where the answers are uncertain and variable. This aspect of AI mimics human cognition to solve problems without clear-cut solutions, combining data from various sources to yield actionable insights. Cognitive computing systems are adept at processing natural language, generating hypotheses, and learning from experiences, which makes them highly effective in sectors ranging from finance to law enforcement. A pivotal component of AI's functionality lies in data processing and analytics. AI systems require substantial amounts of data to learn and make accurate predictions. Big data analytics, the examination of large and varied datasets, allows for uncovering hidden patterns, market trends, customer preferences, and other useful business information. Integrating AI with big data can lead to more sophisticated analytics, as AI technologies can help analyze and synthesize vast arrays of data more efficiently than traditional data analysis methods. AI is also bolstered by advances in hardware. High-performance computing (HPC) systems and graphical processing units (GPUs) provide the computational power necessary for training sophisticated AI models, especially in deep learning. These enhancements in computational capabilities, alongside the development of AI-specific processors and accelerators, have played a crucial role in the rapid evolution of AI technologies. Cloud computing services have democratized access to AI by providing on-demand availability of computer system resources, particularly data storage and computing power, without the user needing to manage the physical infrastructure. Various platforms now support AI application deployment, offering machine learning as a service (MLAAS) for businesses to develop AI functionalities without significant upfront investment in hardware and expertise. Moreover, ethical considerations and the governance of AI are areas that require profound attention. As AI technologies become more embedded in daily life, concerns around privacy, security, accountability, and bias in AI systems are gaining prominence. Establishing ethical guidelines and robust frameworks is critical to ensuring AI progresses in a way that aligns with societal values and norms. The amalgamation of these technologies leverages AI as a powerful tool across sectors. Businesses, governments, and individuals are increasingly reliant on AI to provide efficiencies, insights, and advancements previously untenable. As we explore the multifaceted technologies that constitute AI, it is clear that understanding its elements is essential for mastering its capabilities and unleashing its potential for innovation. 8.2 Cloud-based AI services. The evolution of cloud computing has substantially influenced the development and deployment of artificial intelligence (AI) technologies. Cloud-based AI services provide users with access to powerful computational resources without the necessity of significant capital investment in hardware. These services offer a flexible, scalable, and cost-effective means of leveraging AI capabilities, making advanced AI tools accessible to organizations of all sizes. Through the convenience of the Internet, businesses can tap into the vast repositories of machine learning algorithms, processing power, and data storage offered by cloud service providers. One of the foremost advantages of cloud-based AI services is the democratization of access to machine learning and AI tools. Traditionally, the development and deployment of AI applications required specialized hardware and expertise, barriers that often relegated these powerful technologies to larger, well-funded companies. With cloud-based AI, startups and small to medium enterprises can experiment with and implement AI solutions without the upfront investments in physical infrastructure. This enables a broader spectrum of businesses to develop innovative products and services leveraging AI. Cloud-based AI services are inherently scalable, allowing for the flexible allocation of resources to match the changing demands of AI workloads. For example, an e-commerce business may require increased AI processing power during peak shopping periods to recommend products to customers in real time. Cloud platforms can dynamically allocate more processing power during these times and scale down resources when demand wanes, ensuring optimal utilization and cost efficiency. Scalability ensures that performance does not degrade as the volume of data or the number of users increases, maintaining consistent service quality. The variety of services offered by cloud-based AI platforms is extensive. These services encompass machine learning frameworks, pre-trained AI models, natural language processing (NLP), computer vision, and predictive analytics, among others. Providers typically maintain a suite of tools that companies can integrate into their applications, often with the ease of API calls. For instance, a business can implement image recognition in its app by connecting to a cloud service's pre-trained model instead of developing its proprietary algorithm from scratch. Integration with existing cloud services also amplifies the utility of AI applications. Many organizations already employ cloud services for storage, databases, and software as a service (SaaS) applications. Cloud-based AI services have been designed to work in concert with these existing services, allowing businesses to easily enrich their current technology stacks with AI capabilities. This integration facilitates seamless data flows and interactions between various cloud services and AI functionalities, thereby enhancing operational efficiency and generating deeper insights. Security and privacy are critical concerns when dealing with data and AI. Cloud service providers invest considerable resources to maintain high-level security measures. This includes physical security of data centers, data encryption in transit and at rest, identity management, and compliance with regulations such as General Data Protection Regulation (GDPR) and Health Insurance Portability and Accountability Act (HIPAA). While the responsibility for security is shared with the cloud user, providers ensure baseline protections are in place, which can be more robust than what individual companies could afford on their own. One challenge with cloud-based AI services is the reliance on network connectivity. As the processing of AI workloads occurs remotely, the quality of the service is partially dependent on consistent and fast internet connectivity. Latency can be an issue, particularly when real-time AI decision-making is required. However, advancements in edge computing and the development of 5G technologies are set to mitigate this issue, delivering faster connections and allowing for more processing to occur closer to the data source. Another important aspect of cloud-based AI services is their impact on innovation and the speed of development. By providing developers with pre-built AI services and tools, the cloud accelerates the pace of AI application development. Developers can focus on creating unique features and improving user experiences instead of spending time on the underlying AI infrastructure. This rapid iterative process can lead to quicker deployments, which can provide businesses with a competitive advantage in the market. Cost control is also a significant advantage when utilizing cloud-based AI services. The pay-as-you-go model, typically employed by cloud providers, ensures that companies only pay for the resources they use. This can lead to significant cost savings, as it eliminates the need for over-provisioning, and businesses can avoid the sunk costs associated with depreciating hardware investments. Moreover, companies benefit from the collective advancements in AI made by the cloud service provider, gaining access to continually improving technologies without incurring additional costs for upgrades. Maintaining and updating AI systems can be labor-intensive and technically challenging. Cloud-based AI service providers handle the maintenance and updates of their platforms, ensuring that the latest AI innovations and improvements are readily available to users. This includes patching software vulnerabilities, managing system upgrades, and optimizing the performance of AI models. Users of cloud AI services, therefore, can rely on a stable, up-to-date system without dedicating internal resources to these tasks. The future of cloud-based AI services looks promising, with ongoing advancements in algorithm design, data processing, and machine learning models. As these services become more refined and ubiquitous, we can expect their applications to permeate various industries, driving transformation and enabling new business models. Additionally, the continued commitment to research and development by cloud service providers will likely lead to the emergence of more advanced AI capabilities, further unlocking the potential of cloud-based AI for organizations worldwide. For businesses considering adopting or expanding their AI initiatives, cloud-based AI services represent a crucial opportunity to accelerate innovation, optimize operations, and enhance decision-making processes. The confluence of accessibility, scalability, and cost efficiency afforded by these services underscores their strategic value in today's technology-driven business landscape. As such, a comprehensive understanding of cloud AI capabilities and a thoughtful approach to their integration can prove pivotal in achieving sustainable success in the era of digital transformation. 8.3 Edge Computing in AI. Edge computing refers to a distributed IT architecture where client data is processed at the periphery of the network, as close as possible to the originating source. In the context of artificial intelligence, AI, edge computing plays a crucial role in enabling real-time data processing and decision-making, especially for applications where latency is a critical factor. By minimizing the distance between data collection and data processing, edge computing enhances the performance of AI systems and facilitates the efficient operation of Internet of Things (IoT) devices. The integration of AI with edge computing allows for the deployment of advanced machine learning (ML) models directly onto edge devices. These devices, ranging from smartphones to industrial machinery, can independently execute AI algorithms without the need for constant connectivity to a central server or cloud infrastructure. This shift reduces bandwidth demands on the network and avoids the latency introduced by long-distance data transmission, which is vital for applications such as autonomous vehicles, smart cities, and healthcare monitoring systems. One of the core advantages of bringing AI to the edge is improved privacy and security. By processing sensitive data locally on the edge device, the exposure of this information to external threats during transit is significantly minimized. Edge AI systems can also operate in a semi-autonomous manner, retaining functionality even during disruptions to network connectivity. This aspect is particularly beneficial in scenarios where communication links are unreliable or potentially compromised. To enable AI at the edge, specialized hardware that is capable of running complex AI models with high efficiency and low power consumption is essential. Manufacturers are developing advanced AI chips designed for edge computing, which are optimized for rapid inference and support runtime learning. These chips are embedded into devices to process data in situ, giving rise to a new generation of intelligent and context-aware devices that can adapt to their environment and user behavior. Software is another critical component in the edge AI ecosystem. Lightweight AI models, known as tiny ML, are designed to run on devices with limited computational resources. These models strike a balance between performance and resource usage, making AI accessible on a wider range of edge devices. There are also frameworks and toolkits available, which streamline the process of developing, training, and deploying AI models for the edge, thereby accelerating the development cycle and time to market for AI-powered solutions. In terms of platforms, companies and open-source communities have made significant advancements in creating software that can operate across diverse edge devices. Platforms such as TensorFlow Lite and PyTorch Mobile offer the tools necessary for the conversion of full-scale AI models into versions suitable for edge deployment. These platforms also provide a bridge between edge devices and cloud services, allowing for the continuous improvement of edge AI models through incremental learning and updates. The incorporation of edge computing into AI has given rise to a multitude of new applications. In the industrial sector, edge AI enables predictive maintenance, where sensors on machines run diagnostics in real time, predicting failures before they occur and thereby reducing downtime. In retail, edge AI can be used for personalized in-store experiences, where customers receive targeted information and offers as they interact with store products and services. In healthcare, edge computing helps process medical data directly on wearable devices or local servers, supporting real-time health monitoring and alerting medical professionals to potential issues without delay. For cities, edge AI improves urban management through traffic optimization and energy-efficient lighting systems that react dynamically to the flow of people and traffic throughout the day. Challenges associated with implementing edge AI include ensuring adequate processing power, managing device heterogeneity, and providing continuous power to devices. As such, edge computing devices need to be meticulously engineered to meet the requirements of the specific AI applications they support. Advances in edge AI require interdisciplinary collaboration between hardware engineers, data scientists, and software developers. Future advancements in edge computing and AI will most likely be driven by the continuous miniaturization of hardware, improvements in energy efficiency, enhanced security features, and towards achieving greater interoperability among different devices and platforms. The progression will open up even more possibilities for AI applications and will reshape industries, creating new business models and offering innovative services that were not possible before. Through the convergence of edge computing and AI, it is possible to envisage a distributed network of smart devices capable of localized decision-making. This technological synergy is set to become a cornerstone in the evolution of an interconnected digital world, promoting the development of responsive and autonomous systems that interact seamlessly with their users and environments. As this trend continues, edge AI will become increasingly sophisticated, leading to enhanced user experiences and operational efficiencies across numerous domains. 8.4 Quantum Computing and AI. Quantum computing represents a substantial shift from traditional digital computing. Where traditional computers use bits as the basic unit of information, which can exist in one of two states, 0 or 1, quantum computers use quantum bits or qubits. These qubits exploit the principles of quantum mechanics to exist in multiple states simultaneously, a phenomenon known as superposition. This superposition, alongside another quantum property called entanglement, which correlates the states of two qubits even when separated by large distances, allows quantum computers to process a vast number of possibilities simultaneously. Harnessing these properties allows quantum computers to solve certain types of problems much faster than classical computers. This capability is particularly relevant in fields that require the analysis of large datasets and the execution of complex algorithms, areas where AI is typically applied. Examples include drug discovery, where quantum computers might simulate molecular interactions at an unprecedented scale, and optimization problems across logistics and finance, where they can potentially find solutions far more efficiently than current technologies. The potential synergy between quantum computing and AI is rooted in optimization and machine learning. Quantum algorithms for optimization could revolutionize machine learning by accelerating the process of finding the optimal solution within a model's parameters. This is vital for training deep learning models, as the training process involves searching through a large space of possible model configurations to minimize a cost function. Quantum computers can also perform linear algebra operations, which lie at the heart of many AI algorithms, exponentially faster, which could lead to significant speedups in AI model training. However, this potential comes with challenges. Quantum computers are not only extraordinarily difficult and expensive to build and maintain, they also require a substantial shift in programming paradigms. Current quantum computers are in the noisy intermediate-scale quantum (NISQ) era, a term coined by physicist John Preskill to describe the small-scale quantum processors available today that are powerful yet error-prone. While researchers are making rapid advances in error correction and coherence times for qubits, reliably integrating these systems with AI applications remains a nascent field. Frameworks are being developed to make quantum computing more accessible for AI research. Languages like Qiskit, developed by IBM, and PyQuil, developed by Rigetti Computing, are designed to create and manipulate quantum circuits using a syntax familiar to those who program in Python, a language widely used in the AI community. These frameworks allow researchers to run experiments on simulated quantum computers or even real quantum hardware, available in the cloud. This ease of access is crucial for enabling AI experts without a background in quantum physics to explore the possibilities of quantum AI. One area where quantum computing could significantly impact AI is in the field of optimization. Quantum annullers, like the ones created by D-Wave systems, are designed specifically for optimization problems. Unlike general-purpose quantum computers, quantum annullers use quantum mechanics to naturally find low-energy configurations of a problem, which correspond to optimal or near-optimal solutions. Integrating quantum annullers with AI algorithms could drive advances in fields such as energy management, scheduling, and systems design, where optimization is vital. Quantum computing also promises to enhance AI capabilities in pattern recognition and classification. Quantum feature spaces, which represent data in the high-dimensional space afforded by quantum states, could offer new ways of capturing patterns and correlations in data that are intractable with classical computers. Some researchers propose using quantum-enhanced feature spaces for complex tasks such as image and speech recognition, potentially outperforming classical methods in accuracy and speed. Another promising field of study is quantum machine learning, which explores how quantum algorithms can be used for tasks traditionally performed with machine learning, such as clustering and anomaly detection. Quantum clustering algorithms, for instance, could rapidly group similar data points by exploiting quantum parallelism, while quantum-enhanced anomaly detection can identify outliers in data by processing vast datasets far more rapidly than classical techniques. Despite the potential, there is a significant gap between current quantum computing capabilities and the requirements for practical AI applications. Quantum computers need to become more reliable, less error-prone, and scalable. Significant investment in both hardware and software development is required to bridge this gap. Research into quantum error correction, quantum algorithms, and hybrid quantum classical systems is critical to making quantum AI a reality. Moreover, to integrate quantum computing into mainstream AI research and applications, a multidisciplinary approach involving experts in quantum physics, computer science, and AI is essential. To prepare for the quantum future, companies, governments, and educational institutions are investing in quantum computing research and infrastructure. Partnerships are forming between quantum hardware manufacturers and AI companies to explore new algorithms and applications. Additionally, some universities now offer courses and degrees that combine quantum physics with computer science, aiming to produce a new generation of researchers skilled in both domains. Overall, the integration of quantum computing with AI represents an exciting frontier in technology. While profound challenges must be addressed, the ongoing research and development promise to unfold new capabilities for AI systems. It is a rapidly evolving field that requires patience, investment, and collaboration. With the strides made thus far and the commitment to continued innovation, the future where quantum computing enhances and expands the possibilities of AI appears not just feasible, but inevitable. 8.5 IoT and AI integration. The integration of artificial intelligence, AI, with the Internet of Things, IoT, represents a significant shift in how we perceive and manage interconnected devices. IoT refers to the vast network of devices equipped with sensors, software, and other technologies that allow them to collect and exchange data with other devices and systems over the Internet. When AI is applied to this massive data influx from IoT devices, the potential for smart, autonomous systems grows exponentially, marking a transformative step in various industries. IoT's role is often relegated to data collection and device automation, but the integration of AI transforms these systems into intelligent agents capable of learning from data, making decisions, and predicting outcomes. AI algorithms, particularly machine learning models, can sift through vast amounts of data generated by IoT devices, identifying patterns and anomalies that would be imperceptible to humans. By processing this data, AI can optimize operations, improve efficiency, reduce costs, and enable the development of new products and services. One of the core benefits of integrating AI with IoT is the extraordinary boost in the decision-making process. For instance, in a manufacturing environment, IoT sensors can monitor machine performance in real time. AI can analyze this data to predict when a machine is likely to fail or needs maintenance. This preemptive insight allows for interventions that can prevent costly downtimes, a process known as predictive maintenance. Not only does this improve operational efficiency, but it also extends the lifespan of the machinery. Beyond predictive maintenance, AI-driven IoT systems also have the potential to revolutionize customer experiences. Take the example of smart homes, where AI algorithms can learn a homeowner's habits and preferences, controlling lighting, temperature, and security systems to maximize comfort and energy efficiency. As these intelligent systems learn and adapt, they can provide personalized experiences, often anticipating the needs of the user before they are even aware of them. AI and IoT integration also has implications for smart cities and infrastructure. Urban environments fitted with IoT sensors can benefit from AI to help manage traffic flow, reduce energy consumption, and improve public safety. For example, cameras and sensors can monitor road conditions, while AI can analyze the data to optimize traffic signals, reducing congestion and cutting down on pollution. Moreover, in public safety, AI can analyze footage from surveillance cameras in real time, identifying potential threats and helping authorities to respond more quickly. Another important application of AI in IoT is in the area of healthcare. Wearable devices and medical sensors collect data on patient health metrics around the clock. AI algorithms can process this continuous stream of data to identify health trends, give insights to healthcare providers, and even alert patients and doctors to early signs of health issues before they become serious. This proactive approach to health monitoring can improve patient outcomes and could ultimately lower healthcare costs by preventing avoidable hospital visits and medical interventions. As with any rapidly advancing technology, AI and IoT integration does come with challenges. One primary concern is the privacy and security of the data being collected and processed. The more connected devices we have, the more potential entry points there are for malicious actors. AI can both contribute to this challenge and be part of the solution. It contributes because advanced AI could potentially exploit these systems at a level beyond traditional hacking. On the contrary, it also offers robust anomaly detection capabilities that can identify and thwart security breaches faster than conventional methods. From a technical standpoint, managing the sheer scale of data generated by IoT devices is formidable. AI technologies such as edge computing address this challenge by processing data close to where it is generated, rather than sending everything to a centralized cloud-based system. This not only helps in reducing latency and bandwidth usage, but also supports AI in making more immediate and localized decisions, which is critical for time-sensitive applications like autonomous vehicles or emergency response systems. The integration of AI with IoT also faces a series of ethical considerations. As autonomous systems become more prevalent, questions about accountability and transparency arise. For example, if an AI-driven system makes a decision that leads to a negative outcome, determining responsibility can be complex. Moreover, the potential for AI systems to make decisions based on biased data or algorithms presents significant ethical dilemmas. It is critical that both the data and algorithms are robust, fair, and transparent to avoid perpetuating or exacerbating societal biases. To maximize the potential benefits of AI and IoT, ongoing research and development are essential. Advancements in AI models, along with improvements in sensor technology, communication protocols, and cybersecurity, will continue to expand the capabilities and applications of IoT devices. Cross-disciplinary collaboration among computer scientists, engineers, and industry professionals is critical to fostering innovation while ensuring ethical and secure implementations of these integrated technologies. The symbiosis of AI and IoT is leading us toward a future where technology is increasingly ubiquitous yet unobtrusive, powerfully intelligent yet ideally more intuitive to human needs and contexts. As these systems become more refined and integrated into our daily lives and industries, they promise to offer unprecedented levels of efficiency, convenience, and insight. The full realization of AI's potential in conjunction with IoT will depend on our ability to harness the technology responsibly, innovating inclusively, and addressing the challenges head-on with forward-thinking solutions. 8.6 Open Source AI Tools and Libraries. The progress of artificial intelligence, AI technologies, has been significantly bolstered by the commitment to open-source ethos. Open-source AI tools and libraries provide a collaborative environment where individual developers and companies can build, refine, and optimize AI technologies without incurring high costs associated with proprietary software. This democratization of AI has not only accelerated innovation, but also facilitated the adoption of AI across various sectors. One of the foundational open-source libraries for AI development is TensorFlow. Developed by the Google Brain team, TensorFlow serves as an end-to-end platform that enables developers to easily create and train complex machine learning models. Its versatility stems from its ability to work with multiple CPUs and GPUs, as well as its robustness in handling extensive datasets. TensorFlow's accessible and well-documented nature has made it a staple among machine learning developers and researchers alike. In addition to TensorFlow, PyTorch has emerged as another pivotal tool within the open-source AI ecosystem. It is a library for Python programs that facilitates building deep learning projects. Developed by Facebook's AI Research Lab, PyTorch provides dynamic computational graphing, a feature that allows for more flexible model building and iterative adjustments, an essential aspect of experimental AI research. PyTorch's intuitive interface and ease of use have garnered it a strong following within both academia and industry. Another significant open-source AI tool is scikit-learn. It is built on the foundations of other open-source libraries such as NumPy, SciPy, and Matplotlib. Scikit-learn is designed to integrate seamlessly with the Python scientific computing stack, making it a robust tool for traditional machine learning tasks like clustering, regression, and classification. Many developers prefer scikit-learn for its simplicity and the breadth of algorithms it offers out of the box. The Keras library is another open-source tool that deserves mention. It acts as an interface for the TensorFlow library, allowing for simplified and rapid prototyping of deep learning models. With its user-friendly API, Keras has made deep learning accessible to many who might have found TensorFlow's complexity daunting. Keras is well regarded for its contributions to making deep learning models easier to construct without reducing their power or flexibility. OpenAI, an AI research lab, has also contributed to the open-source community with tools like GIM. GIM is a toolkit for developing and comparing reinforcement learning algorithms. This library provides a wide variety of simulated environments, making it easier for researchers to test their algorithms and advance the field of reinforcement learning. GIM's open-source nature allows for broad collaboration and sharing of reinforcement learning methodologies. Another worth mentioning is the Apache MXNet, a deep learning framework that enables efficient training and deployment of neural networks. MXNet is designed for both efficiency and flexibility, and it scales effectively across multiple GPUs and servers. Oz has chosen MXNet as its deep learning framework of choice, which is indicative of the reliability and performance of this open-source tool. Open-source AI tools also play a crucial role in computer vision applications, with OpenCV being the leading library in this realm. It provides hundreds of computer vision algorithms, including object recognition and image processing, which are invaluable to developers working in fields like autonomous vehicles, security, and augmented reality. In the landscape of natural language processing, NLP, the open-source library NLTK, Natural Language Toolkit, is extensively used. It provides easy-to-use interfaces to over 50 corpora and lexical resources, such as WordNet, along with a suite of text processing libraries for classification, tokenization, stemming, tagging, parsing, and semantic reasoning. This comprehensiveness makes NLTK an essential tool for developers and researchers in the field of NLP. Furthermore, open-source tools extend beyond specific libraries and into platforms like Jupyter. Jupyter Notebooks provide an interactive computing environment where researchers and developers can mix executable code, visualizations, and narrative text. The platform has become a vital tool in the data science community for developing, documenting, and sharing code for AI applications. Lastly, open-source contributions to AI aren't just limited to individual tools, but also encompass entire platforms such as the Open Neural Network Exchange, ONNX. ONNX provides an open standard for representing machine learning models that allow developers to move models between different AI frameworks seamlessly. This interoperability is crucial for the AI development process, as it mitigates the issue of software lock-in and fosters a more inclusive environment for innovation. The proliferation of open-source AI tools and libraries marks a significant chapter in the development and application of AI technologies. These resources have lowered the barriers to entry for both novices and seasoned professionals, catalyzing exploration, education, and progress. As these tools continue to evolve, driven by a worldwide community of collaborative contributors, we can expect the bounds of what is possible with AI to expand accordingly. Their collective impact is one of the defining strengths of the AI field, offering a diversity of options that can suit a wide array of applications and encouraging constant advancements through shared challenges and results. 8.7. AI hardware, GPUs and TPUs. AI hardware forms a critical foundation for the development and deployment of machine learning models and AI applications. The demand for efficient and high-performance AI hardware is driven by the increasing complexity of AI algorithms and the massive volumes of data they process. Two pivotal components in this landscape are graphics processing units, GPUs, and tensor processing units, TPUs. This section delves deep into the roles, functionalities, and implications of GPUs and TPUs in the sphere of AI and blockchain technology. GPUs, originally designed for rendering graphics in video games, have architecture that suits parallel processing tasks. Their capability to handle multiple operations simultaneously makes them ideal for the matrix and vector computations common in deep learning and other AI workloads. GPUs are equipped with hundreds to thousands of cores, which allows them to process many threads concurrently. This attribute is particularly useful in training neural networks, where the same operation is repeated over each element in a dataset. Modern GPUs also feature high memory bandwidths to keep their many cores supplied with data, effectively reducing bottlenecks and increasing computational throughput. In contrast to GPUs, TPUs were explicitly crafted to accelerate machine learning tasks. Google introduced TPUs to optimize their data centers for AI computation, responding to the growing need for specialized hardware that could efficiently process neural network-based applications. TPUs are application-specific integrated circuits, ASICs, optimized for the tensor operations which are fundamental to deep learning algorithms. Their architecture enables higher precision calculations, essential for accelerating the training and inference phases of machine learning. With a design focused on matrix operations, TPUs outpace GPUs in certain AI tasks by executing them more efficiently and at lower power consumption levels. While GPUs are versatile, supporting a broad range of AI applications and other parallelizable tasks, TPUs are somewhat less flexible, being tailored for a specific realm of machine learning operations. However, this specialization allows TPUs to offer superior performance for their intended tasks. When comparing TPUs to GPUs, it is essential to consider the specific use case. For general-purpose AI workloads, GPUs may be the better choice, but for large-scale and optimized machine learning projects, TPUs could offer significant advantages in terms of speed and cost efficiency. The development of AI models in blockchain technology can benefit from the use of GPUs and TPUs in several ways. First, the cryptographic computations required for mining and for executing smart contracts are remarkably parallelizable, which GPUs can efficiently process. Second, for blockchain networks that utilize AI algorithms for pattern recognition, fraud detection, or decision-making, the capabilities of GPUs and TPUs to rapidly train and deploy AI models can facilitate these tasks. Moreover, TPUs can drive the performance of on-chain AI applications by accelerating the inference tasks directly on the blockchain network. Despite the advantages, there are also challenges associated with using GPUs and TPUs for AI in blockchain. The high cost of these units can be a barrier for smaller enterprises or individuals looking to experiment or develop small-scale applications. Additionally, the technical complexity of programming and maintaining systems that utilize these components can require significant expertise. Additionally, integrating AI hardware into a decentralized technology like blockchain might introduce centralization points, which could be seen as contrary to the principle of the decentralization ethos, which is central to blockchain technology. AI hardware choices can be influenced by scalability concerns as well. As blockchain networks grow and as the AI models become more complex, the ability to scale AI hardware effectively can significantly impact performance and maintenance costs. GPUs are typically easier to scale, as they can be added to existing systems reasonably seamlessly. However, integrating TPUs into scalable systems presents more of a challenge due to their specialized nature and the infrastructure originally designed by Google for their data centers. Energy consumption is another critical factor in the discourse about AI hardware in blockchain technology. The energy intensity of AI computations, especially during the training phase, is substantial, and when combined with the energy requirements of running a blockchain, the carbon footprint can become a concern. GPUs and TPUs are becoming more energy efficient with each generation, yet the conversation around sustainability continues to drive the pursuit of even more energy-efficient technologies, perhaps leading to the development of new categories of AI hardware in the future. Manufacturers of AI hardware are constantly innovating to keep up with the rapid advancement of AI and blockchain technology. NVIDIA and AMD are examples of companies advancing GPU technology, while Google continues to enhance TPU capabilities. These advancements aim to provide more power-efficient hardware with greater computational capacity, thus supporting the increasingly complex demands of AI applications. In particular, the release of tensor cores within GPUs and the iterative improvements in TPU design both serve to improve the efficiency and performance of machine learning tasks. Future trends in AI hardware may see further specialization, with new types of processing units being developed for different kinds of AI tasks. As blockchain technology matures and its integration with AI becomes more profound, we can expect that the hardware underpinning these technologies will also evolve. Hybrid systems that combine the flexibility of GPUs with the efficiency of TPUs, advancements in neuromorphic computing, and quantum computing are some of the exciting prospects in the evolution of AI hardware. In the broader context of blockchain and AI integration, GPUs and TPUs represent a critical juncture in the technological advancement. Their role is paramount in enhancing the capabilities of AI, which in turn enriches the functionalities and efficiencies of blockchain networks. As blockchain protocols begin to incorporate more AI functionalities directly on-chain, the importance of optimized AI hardware will only grow. Finding the right balance between general-purpose computation and task-specific acceleration will continue to be a significant factor in the design and deployment of these technologies. Ultimately, the advancements in AI hardware, particularly GPUs and TPUs, will dictate the pace and scope of future innovations in blockchain technology. 8.8 AI platforms for developers. As has often been the case throughout technological history, tools and platforms that simplify complex processes have become essential for widespread adoption and innovation. In the realm of artificial intelligence, AI, this trend is particularly marked. Developer-centric AI platforms are software tools that abstract away much of the complexity involved with machine learning, ML algorithms, data processing, and neural network design, allowing software engineers and developers with varying degrees of expertise in AI to create intelligent applications. These platforms range from cloud-based services to frameworks that can be run on personal machines. One prominent characteristic of developer-focused AI platforms is their propensity to offer pre-built algorithms and models. These pre-configured systems can recognize images, understand spoken language, and even interpret complex data patterns. This ease of access allows developers to integrate sophisticated AI capabilities into their projects without the need to develop the underlying algorithms from scratch. Moreover, these platforms generally provide thorough documentation and active user communities, which are indispensable resources when one is learning how to effectively implement AI in various contexts. Leading the charge in this domain are major cloud providers like Amazon Web Services, AWS, Google Cloud, and Microsoft Azure. Each offers a suite of AI services designed to cater to a broad range of needs. Oz, for instance, has a selection of services under the Amazon AI umbrella, including Amazon Lex for building conversational interfaces, Amazon Poly for text-to-speech applications, and Amazon Recognition for image and video analysis. These services are accessible through the AWS Management Console, and developers can control them through standard AWS SDKs or by using APIs. Google Cloud's AI platform similarly provides an array of machine learning services, with Google's AI Hub serving as a repository for high-quality plug-and-play machine learning content. It includes deep learning VM images for computational scalability and supports a wide range of ML frameworks like TensorFlow, PyTorch, and scikit-learn. The platform also integrates with Google's data services and offers tooling for machine learning workflow automation, making it a powerful resource for end-to-end development in the AI space. Microsoft Azure's AI capabilities are incorporated into its broader set of cloud services, with products such as Azure Machine Learning Service, a workspace for training, deploying, automated machine learning workflows, and managing ML models. Perhaps one of the more intriguing offerings is Azure Cognitive Services, a collection of APIs that enable developers to incorporate intelligent features such as emotion and sentiment detection, vision recognition, and language understanding into their applications. IBM's AI platform, Watson, is another pivotal player, which offers a range of services, including natural language processing and conversation services. Watson can be integrated into cloud-based applications or deployed on-premises, offering flexibility depending on organizational needs and security requirements. It also emphasizes strong learning capabilities, allowing models to improve over time as they are exposed to more data. Open-source frameworks also play a critical role for developers looking for customizable and potentially cost-effective solutions. TensorFlow, an open-source software library for data flow and differentiable programming, was developed by researchers and engineers from the Google Brain team. Its flexible architecture allows developers to deploy computation to one or more CPUs or GPUs, making it a highly versatile tool for a range of AI applications. Another open-source tool, PyTorch, emphasizes ease of use and flexibility in deep learning and has gained popularity for its dynamic computational graph and efficient memory usage. Beyond these foundational platforms, there exist numerous specialized AI tools targeted towards niche application domains. For example, H2O.ai specifically targets data scientists with a penchant for machine learning and data analysis, offering automated ML tools that streamline the process from data import to deployment. OpenAI, another prominent organization in the AI space, provides GIM, a toolkit for developing and comparing reinforcement learning algorithms. Developer platforms not only provide the building blocks for building AI-driven applications, but also the infrastructure for model training and deployment. For instance, services like Google's Vertex AI and Amazon's SageMaker abstract away much of the complexity of provisioning hardware and managing server clusters necessary for training large machine learning models. These managed services include capabilities for continuous integration and delivery, CI/CD, of AI models, monitoring, and A/B testing, which are vital for maintaining robust AI systems in production. Lastly, developer-centric AI platforms often feature a pricing model that scales with usage, which can be a boon for small teams and startups. Flexible pricing ensures that developers can begin experimenting with AI with minimal initial investment, scaling up costs as their application's user base grows or as their processing needs become more demanding. AI has reached a point where the foundational technologies are not only powerful, but have also been encapsulated in user-friendly platforms, accessible to developers at all skill levels. Advancements in this area will likely continue to accelerate, reducing the barriers of entry for AI and enabling a new wave of intelligent applications. These platforms serve as the workbenches upon which the future of technology is being built, one line of code at a time. 8.9 Integrating AI into existing systems. Integrating artificial intelligence, AI, into existing systems is a significant step for many organizations aiming to enhance efficiency and gain insights from their current operations. While AI offers transformative potential, merging it with legacy systems can be a complex process that demands careful planning and execution. The first step in this process is to conduct a thorough assessment of the existing infrastructure. This involves a close examination of hardware, software, data flows, and processes to identify areas that can benefit from AI capabilities. For many, this might be data-heavy sections like customer relationship management (CRM) systems or resource planning platforms. Once existing systems are assessed, the next phase is to establish clear integration goals. These objectives should be aligned with the business strategy and take into account both the current needs and future growth potential. Setting concrete goals will establish benchmarks for success and guide the selection of appropriate AI technologies. For instance, if the goal is to improve customer support, an AI solution that includes natural language processing (NLP) to interpret and respond to customer inquiries might be sought. This goal-oriented approach ensures that the integration of AI is strategic and purpose-driven. The integration generally requires selecting the right AI technology that is compatible with the existing infrastructure. This decision must be informed by the system's specifications, as well as the software's scalability, interoperability, and compliance with industry standards. Not all AI solutions are created equal, and some may necessitate additional hardware upgrades or software patches. Selecting the right AI solution might also entail choosing between a custom-developed AI application or an off-the-shelf product. An in-depth cost-benefit analysis often aids in making this crucial decision. After selecting the appropriate AI technology, one must focus on the integration process itself, which might involve building APIs or developing middleware to ensure seamless communication between the AI application and the existing systems. This technical task should be handled by skilled IT professionals, following best practices in software development and integration. Thorough testing is imperative at this stage to identify and iron out any bugs or compatibility issues that could disrupt business processes. Another important aspect of the integration process is data management. AI systems typically require significant amounts of data to learn and make intelligent decisions. Therefore, an organization must ensure that their existing data is clean, organized, and accessible. If data is siloed or of poor quality, then data integration and preparation tasks must be undertaken to create a consistent, high-quality dataset. This might include data cleaning, deduplication, and format standardization. Integration goes beyond technical execution. Staff training also plays a pivotal role in the success of AI deployment. Employees must be equipped with the knowledge and skills to engage with the new AI-enhanced system effectively. Training programs can vary, from teaching basic AI concepts to providing detailed instructions on interfacing with the new system. Additionally, addressing any concerns or resistance from staff members by highlighting the benefits and opportunities AI brings can facilitate smoother adoption. With successful integration of AI into legacy systems, attention shifts to continual monitoring and evaluation. The organization should have mechanisms in place to measure the performance impact of AI. This analysis helps to determine if the integration is meeting predefined goals and delivering the expected benefits. Moreover, it reveals areas where AI could be better leveraged or where its application may be expanded. This cycle of monitoring and assessment is vital for long-term sustainability and optimization of AI within an organization. Security considerations must also be high on the agenda when integrating AI into existing systems. As AI systems process and store large volumes of sensitive data, ensuring data privacy and protection is crucial. It includes implementing advanced security protocols, undergoing regular security audits, and ensuring that AI solutions comply with data protection regulations such as GDPR. Safeguarding against security threats not only protects the organization's data, but also maintains the trust of customers and partners. One must also account for scalability when incorporating AI into systems that already exist. As the business grows and evolves, so will its data processing needs and the complexity of queries that the AI must handle. The chosen AI solution should be scalable to accommodate increased workloads and more advanced analytics without requiring a complete overhaul. An eye for future-proofing during the integration phase can save considerable time, effort, and resources down the line. Finally, maintaining flexibility and adaptability throughout the integration process cannot be overstated. Technology and business environments are continually evolving, which may necessitate adjustments to both the existing systems and the AI solutions in place. A successful integration is not just about the initial implementation, it's also about establishing a framework that allows for ongoing adjustments and improvements as required by changing circumstances. The integration of AI into pre-existing systems marks a crucial milestone in an organization's digital transformation journey. While it empowers businesses to redefine their workflows, enhance data-driven decision-making, and stay competitive, the undertaking is multifaceted and requires a meticulous and adaptive approach. By thoughtfully planning every step, from evaluating current infrastructure and setting goals to training staff and maintaining security, businesses can successfully harness the power of AI and ensure that their investment delivers tangible and lasting benefits. Each stage builds on the premise that AI should not displace existing frameworks but rather extend and enrich them, creating a more intelligent and responsive enterprise. 8.10 AI as a Service, AIaaS. The concept of AI as a Service, AIaaS, entails the offering of artificial intelligence outsourcing by providing clients with access to AI tools and frameworks without the high initial investment and the need for deep technical expertise. By utilizing AIaaS, companies can deploy machine learning models, natural language processing, image recognition, and other AI functionalities through cloud platforms. This model allows businesses to experiment and innovate with AI capabilities while minimizing risk and reducing the barrier to entry. Businesses that leverage AIaaS can tap into sophisticated AI capabilities without hiring a team of data scientists and machine learning experts. A wide range of services is provided through subscription-based models, pay-as-you-go plans, or usage-based pricing, which offers flexibility and scalability. Companies can choose from various AI services that fit their specific needs, enabling them to enhance customer experiences, optimize operations, and create new revenue streams. The proliferation of AIaaS is largely driven by major tech companies that have developed robust AI and cloud computing infrastructures. These AIaaS providers, such as Amazon Web Services, AWS, Microsoft Azure, Google Cloud, and IBM Cloud, offer a suite of pre-built AI tools and services. These platforms are equipped with user-friendly interfaces that allow non-experts to build, train, and deploy AI models with relative ease. The services within AIaaS cover a wide range of machine learning capabilities and use cases. Examples include image and video analysis, where AI models are trained to recognize objects, faces, or scenes. Text analytics and natural language services can interpret and understand human language, enabling sentiment analysis, language translation, or chatbot development. Furthermore, predictive analytics services can forecast trends and behaviors by analyzing large datasets, providing critical insights for decision-making processes. Another significant advantage of AIaaS is that it provides the computational power necessary for processing large datasets and complex algorithms. By harnessing the cloud's resources, AIaaS eliminates the need for businesses to invest in expensive hardware. Clients can access high-performance computing power on demand, with the flexibility to scale up or down based on current project requirements, ensuring efficient use of resources and cost savings. Security and privacy are considerations that AIaaS providers prioritize. The data used in AI services must be handled with the utmost care, as any breach could have severe consequences. AIaaS platforms employ advanced security protocols, data encryption, and compliance with international standards to protect sensitive information. Clients can thus focus on their core operations, knowing that their data is secure within the AIaaS system. To facilitate the development of AI solutions, AIaaS platforms often provide documentation, tutorials, support forums, and customer service to aid users throughout the lifecycle of their projects. This support system is crucial for enabling companies that may not have extensive AI expertise to begin implementing complex AI systems. Furthermore, AIaaS providers frequently update their offerings to include the latest advancements in AI research and technology, ensuring that clients have access to state-of-the-art tools. Moreover, AI enables businesses to engage in ethical and responsible AI practices. Providers often incorporate tools for bias detection and mitigation, ensuring that AI systems operate fairly and without discrimination. The shared responsibility model also means that AI providers are invested in maintaining the integrity of their services, as their reputation hinges on the reliability and ethical standards of their platforms. Industries ranging from healthcare to finance, retail to manufacturing, are adopting AI to drive innovation without the full-scale commitment of building in-house capabilities. In healthcare, for instance, AI enables providers to implement diagnostic tools and personalized treatment plans with greater accuracy and speed. In finance, fraud detection algorithms powered by AI can analyze transaction patterns in real time to prevent financial crimes. As AI continues to evolve, the landscape of AI is likely to broaden further, incorporating newer AI paradigms such as reinforcement learning, generative adversarial networks, and quantum machine learning. As the technology becomes more pervasive, compliance with evolving regulations will become more complex. AI providers will play a pivotal role in navigating these challenges, providing their clients with guidance and services that are compliant with local and global regulations. The continuous development and refinement of AI signify a commitment to democratizing access to artificial intelligence. Small to medium-sized enterprises stand to benefit immensely as AI levels the playing field, allowing them to compete with larger corporations that have more resources. The dexterity that AI offers spells unparalleled potential in optimizing business processes, tailoring customer experiences, and spearheading automation across various sectors. In essence, AI as a service embodies a transformative shift in how artificial intelligence is consumed and applied in the business world. By abstracting the complexities involved in developing and deploying AI, and by presenting it in a more accessible and flexible manner, AI not only accelerates the adoption of AI across industries, but also serves as a catalyst for continuous innovation and competitive edge in the digital era. With AI the integration of artificial intelligence into the fabric of business operations becomes less of an intimidating venture and more of a strategic imperative, as organizations strive to remain relevant and efficient in an increasingly AI-driven marketplace.